Okay, everybody. Sorry about that. I guess when I got that phone call, it stopped my video. So we're going to pick up with number 6. Some of this will be a little bit of duplication. Sorry. So we're trying to find the energy, the bond energy in this triple bond between the carbon and nitrogen atom. So when we're using the bond energies, we're usually solving for delta H, but in this case we know delta H, and our unknown is this bond energy here. So we're just going to call this unknown X. Okay, so bond energies, again, it's my reactants minus my products. So my delta H is negative 137 kilojoules. Okay, my reactants, I have one single bond between hydrogen and carbon. So that is 1 times the 410. Actually, I need to go back to my table. I'm on the wrong page now. Okay, 410 kilojoules per mole. And then here's my X, so I'm going to add in this 1 mole of my triple bond, but I don't know what that value is, so that's just X. Plus I have 2 single bonds between hydrogen atoms, so 2 of those, 436 kilojoule per mole. And then I'm going to subtract out all my bonds over here in my products. Okay, now there's a lot of bonds in my products, so I'm going to use a red pen to keep track of which one I've subtracted so far. So I have 3 hydrogen hydrogen carbon bonds, 3 of these. If I look up a single bond between hydrogen and carbon, that's 410 kilojoule per mole. And then again, I'm subtracting out, I have 1 single bond between carbon and nitrogen. So that is 300 kilojoule per mole. And then I have 2 bonds that I'm forming between nitrogen and hydrogen, a single bond between nitrogen and hydrogen, which is 390. Okay, so these coefficients in front cancel out my moles. Okay, so if I simplify some here, I have 137 kilojoules on the left. And then if I multiply these things out, 1 times 410 is obviously 410 kilojoules, plus my X, I don't know what that is yet, plus 2 times 436 is 872, and then minus 3 times 410 is minus 1230, minus 300, minus, this is 780, and these are all kilojoules. Should have been writing the units down. So then this is kilojoule, kilojoule, kilojoule. All right, so my left side remains 137 kilojoule. My right side then ends up being X, and when I combine like terms, I will have X minus 1028 kilojoule. So then to solve for X, I just add 1028 to each side, and I end up with X equals 891 kilojoule per mole. Okay, so nothing really new except that normally we're solving for delta H. In this case, we were given delta H and we need to solve for one of the bond energies. So again, we still just have one unknown. It's just a little bit different algebra. Okay, moving on to number 7. What is the standard enthalpy of formation for iron solid? Okay, so the standard enthalpy of formation is again this symbol, and we want to know what that is for iron solid. And in this case, the answer is easily 0. And we know this is 0 because with these standard formation enthalpies or entropies or any of those, whenever it's a standard formation, which is what this little F stands for, anything in its natural state they equal 0. So again, iron is naturally in its solid state. A couple other ones that are going to be common to see are your diatomic molecules, your homonuclear diatomic molecules, like oxygen gas, hydrogen gas. These, the standard enthalpy of formation would also be 0. Okay, number 8. What is the delta H for the complete combustion of C6H6 liquid at 25 degrees Celsius and use Hess's law? Okay, so we first of all need to figure out the balanced chemical equation. So I'm going to have my C6H6 plus oxygen gas, and that's going to yield carbon dioxide gas plus water vapor. Okay, and this is not a balanced chemical equation, so I need to balance it. And when I balance it, I would end up with a 2, 15, 12, and 6. Okay, we're not going to go through how to balance that. I'm assuming you know how to do that now. Okay, and they want to know delta H using Hess's law. Well, delta H, we're going to take all the products and subtract the reactants. Okay, so all the products, the delta H of formation, times all the delta H of formation of the reactants. Okay, so we'll start here with our products. I have 12 moles of carbon dioxide gas. If I look up carbon dioxide gas in my table of my entropies, standard entropy of formation, I find that that is minus 393.5 kilojoules per mole. I still have another product, so I'll add that, 6 moles of water vapor. If I look that up on my table, 241.8 kilojoules per mole. Done with my products, so I'm going to move my reactants. Again, I subtract my reactants, so negative 2 moles times my C6H6 liquid, which is 49.0 kilojoule per mole. And then my oxygen is in its natural state, O2 gas, so this is just 0. So I don't need to worry about that one really much. Okay, so if I do my math out then, my delta H, 12 times this is negative 4,722.0 kilojoule because the moles cancel. And then I'm going to have 6 times negative 241 is going to be a negative 1450.8 kilojoule. And then negative 2 times 48 is negative 98.0 kilojoule. Again, the moles cancel out. And if I do all that math out, I end up with my delta H is equal to negative 6,270.8 kilojoule. Okay, number 9. Okay, so number 9 says the delta H for the following reaction is, so this one's giving me delta H is 157.9 kilojoules at 25 degrees Celsius. So when we see this at 25 degrees Celsius, I know that I can use my standard enthalpy of formation values. And it wants to know what is the standard enthalpy of formation of the H2S liquid. So let's look at the chemical equation. I have carbon in the form of graphite plus 2 of my H2S gas yields CS2 gas plus 2 H2 gases. All right. So I know my standard enthalpy of formation, so 157.9 kilojoule, and then I'm going to take my products minus my reactants. Well, in this case, I have two things that are in their natural state that I know are going to net to zero, my H2 gas, and the problem tells us that carbon, that graphite, is the natural phase, so I don't need to worry about this one. So things become pretty simple. And this is the one I'm trying to find. So I'm going to let this one equal X, my unknown. Okay, so my product is CS2 gas. I have 1 mole of that. CS2 gas is, what number am I on here? 116.9 kilojoule per mole. And then I'm going to subtract my reactants. Again, my carbon graphite is in its natural state, so I don't need to worry about it. I have 2 moles of my unknown. So I'm just going to use X for my unknown. I can simplify this a little bit. 157.9 kilojoules equals, here my moles cancel out, so 116.9 kilojoules minus 2 moles times X. Okay, I'm going to subtract 116.9 from each side. If I do that, I end up with 41.0 kilojoules equals negative 2 moles times X. So I will divide each side by negative 2 moles. And if I do the math out, I end up with negative 20.5 kilojoule per mole equals X. And that is the standard enthalpy of formation of my H2S gas. Okay, so same type of problem using Hess's law. It's just instead of solving for the standard enthalpy, or sorry, the change in enthalpy, we're solving for one of the other unknowns. Okay, number 10, given the problem, the information in number 9, so 10 is building on number 9, how much energy would it take to make 100 grams of the CS2 gas? Okay, so we know that this equation here, the delta H, or the change in entropy, change in enthalpy, is 157.9. So we know that it is absorbing energy. It's an endothermic reaction. So what's an endothermic reaction? We have to take energy from the environment and use it as a reactant. So we can just write it in our equation up here as a reactant. Okay? So another thing we know is that the grams aren't going to do us much value here, so we need to convert these grams to moles. Okay, and we've done this many, many times. You look on the periodic table and you figure out that a mole of CS2 gas has 76.13 grams. So our grams cancel out, and if we do the math, we end up having 1.314 moles of CS2 gas. Okay, so 100 grams is the same as 1.314 moles. Okay, so we have 1.314 moles of CS2 gas. And then this, we're just going to use some stoichiometry, okay? If we look back at our balanced chemical equation, we know for every 1 mole of CS2 gas, we need 157.9 kilojoules. Well, now my moles cancel out and I'm left with kilojoules, which is what I want. So I just multiply 1.314 times 157.9, and if I do that out, I end up with 207.5 kilojoules. So to get 100 grams of the CS2, we would need to add 207.5, or we would need 207.5 kilojoules of energy. Now there was a video that talked pretty exclusively about how to do problems like this. So if you're still confused about number 10, go back and look at some of the videos. All right, number 11. Let's just move to a new sheet of paper. Number 11 is drawing these reaction coordinate diagrams. Now remember, for each of these, you'll have energy on the y-axis and the reaction on the x-axis, and this reaction is similar to time. Okay, so 11A says it's an exothermic reaction with a high activation energy that releases a small amount of energy. Okay, so if it's exothermic, that tells me energy's being released. So my products will have less energy than my reactants. So my reactants are going to start at a higher level than my products end up at, because I'm releasing energy. Okay, this also tells me there's a high activation energy, so that means that hill that represents the activation energy is going to be pretty high. Okay? And it tells me it releases a small amount of energy, so actually I'm going to draw my products about here. So again, these are my reactants, these are my products. The difference between the energy of my reactants and the top of the hill is my activation energy. All right, and the difference between where my products end up and my reactants start is my delta H. So this shows that it releases, we'll say this is a relatively small amount of energy. So it needed a lot of activation energy, so my hill is tall, and my products ended up somewhat lower than my reactants, but not a lot lower. Okay, let's quickly look at letter B. Again, here's my axis. This time it's an endothermic. So my products will have more energy than my reactants because they absorbed some energy. And the activation energy is only a little bit larger than the delta H. Okay, so in this case then, here's my reactants. I add some activation energy, okay? And I know that my activation energy isn't much different than my delta H. So my products are gonna end up here. So again, if I look, here's my activation energy. And here's my delta H. Because again, activation energy is from where I start with my reactants to the top of the hill. My delta H is the difference between my reactants and my products. And in this case, there's not much difference between the top of my hill to where my products end up. And then lastly, on letter C, it's a reaction that's easier to start than reaction A. So that tells me I don't need as much activation energy. Okay, so my hill isn't going to be as tall, but it releases more energy. So that means my products end up much lower than my reactants. So this is the amount of energy that's released. So that's greater than what I had in letter A. And this is my activation energy, which is not very tall. Okay. All right, 12. 12 starts talking about, let me turn my page here. 12 starts talking about entropy. Okay, remember, entropy is very similar to disorder. And in this case, it's going to give us 4 examples, and we need to pick the situation that has more entropy or more disorder. Okay, so letter A says a vase sitting on a shelf, or that same vase that's broken into many pieces. Well, the broken vase would illustrate more disorder. Letter B, a sample of water as a liquid at 0 degrees Celsius, or the same mass of water as an ice cube at 0 degrees Celsius. So same temperature, same substance, but one is liquid and one is solid. So the liquid is going to have more disorder. Anything in the liquid is moving around more rapidly than something in a solid state that's only allowed to just vibrate. Letter C, a copper pipe that is cold, or the same copper pipe that is hot. So again, same substance, this time they're in the same phase. They're both solid, but one is cold and one is hot. So the hot substance will have atoms that are moving more rapidly than the cold. So the hot will be more disordered. And then letter D, a bunch of confetti scattered evenly on the floor of a 3 by 3 meter room, or the same amount of confetti scattered evenly on the floor of a 2 by 2 meter room. So this gets to distribution. And the more distributed things are, the more disordered they are. It would take more time for you to pick up the confetti in a 3 by 3 room than it would be for you to pick up and make orderly the confetti in the 2 by 2 room. So in this case, there's more entropy in the 3 by 3 room. Okay, 13. A student says that because a chemical reaction has a negative delta S, it cannot be spontaneous. Is this correct? Why or why not? Okay, so a negative delta S, or a negative change in entropy, tells us that entropy is decreasing, which means that it's becoming more organized. Remember, entropy is disorganization. So if the disorganization is decreasing, the system's actually becoming more organized. So this may be spontaneous if the surroundings are becoming more disorganized than the system is becoming organized. Remember, when we talk about spontaneity or the spontaneous, whether a chemical reaction is spontaneous or not, we need to look at the surroundings and the system. Okay? And a reaction is spontaneous if the surroundings and the system, if their change in entropy is less than 0. So while the system may be becoming more organized, the surroundings may become so disorganized that we still end up with a value that's less than 0. If the surroundings are becoming more disorganized, then the system is becoming organized. So hopefully that makes sense. So is he correct? The answer is no, he's not correct, and this is why. Okay, number 14, we need to just determine the sign for the change in entropy for the following reactions. So when we're talking about change in entropy and the sign, there's 2 things we're going to look at. We're going to look at phase, and if the phases are all the same, then we're going to look at the number of molecules. Okay, so let's look at 14A. It's 6 CO2 gas plus 6 H2O gas yields glucose solid plus 6 O2 gas. So we have 2 gases going to a solid plus a gas. So obviously this solid is becoming more organized. I can look at the phase here. So the solid's becoming more organized. So the entropy is actually decreasing. This system is becoming more organized. So that means our delta S would be less than 0. Okay, letter B, we have a gas and a gas. One gas plus a gas yields a gas. So all the phases are the same. So this isn't really helping us to look at phase, but I can look, I have one gas molecule here, I have two gas molecules here, and I'm producing only one gas molecule. So on this side I have 3 molecules, and my products are only 1 molecule. So my number of molecules is decreasing. So this system's becoming more organized, and again, my entropy is decreasing then. So my delta S would be less than 0. Finally, letter C, I have a solid plus an aqueous yielding an aqueous plus a gas. So I can look at just the phases. I have a solid and a gas, so obviously this is becoming less organized. So the entropy is increasing. So my change, my delta S, or change in entropy, is greater than 0. Okay, number 15, we're going back to that same combustion problem that we had in number 8. It says in number 8 we calculated the change in enthalpy. Now we're going to calculate the change in entropy. Okay, so the change in entropy, sorry, I got distracted by something. We need to start with our that same equation. So 2C6H6 liquid plus 15 O2 gas yields 12 CO2 gas plus 6 H2O gas. And this time I'm calculating my change in entropy using the technique of Hess's law. So again, I'm going to take my products minus my reactants. So let's start over here with our products. I have 12 moles of the CO2 gas, which is 213.7 joules per mole K. And then I have 6 moles of my water vapor, which is 188.7 joules per mole K. So I've accounted for both of my products. Now I'm going to subtract my reactants. So minus 2 moles of my C6H6 liquid, which is 173.4 joules per mole K, minus my 15 moles of O2 gas, which is 205.0 joules per mole K. All right. And if I do all that out, I'm assuming that you can do all this algebra, I end up with a delta S of 274.8 joules per K. All right, number 16, use Hess's law technique to calculate delta G of the complete combustion of this same reaction. I just realized when I was doing this, I did not use the Hess's law technique. I used Gibbs free energy. So let's use Hess's law instead. So again, I'm looking at this same, instead of rewriting it, I'm looking at this same chemical reaction, but now I want to calculate the delta G. So I need to use my table of the standard Gibbs free energies of formation, which is on page 444. This is going to take me a little bit longer because I don't have this one done out. Okay, again, starting with my products. It's always products minus reactants, except for bond energies. So I'm going to start with my products. I have 12 moles of CO2 gas. So I look up my CO2 gas in the table, minus 394.4. Kilojoule per mole. Okay, plus I have 6 moles of water vapor. Okay, water vapor minus 228.6 kilojoules per mole. Then I'm going to subtract out my reactants, so minus 2 moles of C6H6 liquid, 124.4 kilojoule per mole. And then I have oxygen gas. Now remember, because this is a energy of formation, I don't need to spend any energy forming O2 gas. It already exists like that in its natural phase, so this is just 0. Okay, and I don't have the answer in front of me, but I'm assuming you guys know how to do this math out, but this is how you would set up the problem. Okay, number 17. So number 17, we have the delta H and S of several reactions, and we need to determine if they're spontaneous or not. Okay, so 17A. Let's look at 17A. Now remember, the Gibbs free energy tells us that delta G equals delta H minus T in Kelvin times delta S. Okay, in 17A, we have a delta H of 146.1 kilojoules. We have delta S is 86.1 joules per K. Okay, so both of these are positive, and because they're both positive, we don't know if delta G will actually end up being positive or negative, so we need to do the math out. Okay, now the first thing we need to do is convert these so the units are similar. So we're going to convert kilojoules to joules, so that's 146,100 joules. And we know for a reaction to be spontaneous, delta G needs to be less than 0. So this value here needs to be less than 0. So delta H minus T delta S has to be less than 0 for this reaction to be spontaneous. So now we can just plug in our values. Delta H is 146,100 joules minus T, which is what we don't know, we're solving for. My delta S is 86.1 joule per K, and this must be less than 0 for it to be spontaneous. So how do we solve for this? I'm going to add this term to both sides. 146,100 joules stays here. I keep my less than sign, and this moves to the other side. Now to get T all by itself, we divide both sides by 86.1 joule per K. 86.1 joule per K. So this cancels out, and on the right, I'm just left with T. Over here, my joules cancel out. My unit is K, which is what I want. And I should end up with 1,696 K. So as long as my temperature is above 1,696 K, this reaction will be spontaneous. Anything below this, it will not be spontaneous. All right, let's look at B. We have a delta H of negative 115.2 kilojoule and a delta S of 97.3 joule per K. Yeah, backwards, joule per K. Okay, I'm going to convert this to joules, so that's negative 115,200 joules. So put this in my equation. I have negative 115,200 joules minus whatever my temperature is, and then times 97.3 joules per K. And actually, I don't even need to go any further here because I have a negative and another negative, so no matter what I do, delta G is going to be negative. No matter what my value for T is here, my delta G is going to be negative. So this one will always be spontaneous. I don't need to worry about what my temperature is. All right, let's look at letter C. Delta H is 219.5 kilojoule, which is the same as 219,500 joule. Delta S is minus 99.9 joule per K. So my delta G then is 219,500 joules minus some temperature times minus 99.9 joule per K. All right, this one I do need to do a little bit more work because, well, actually, no, I don't. I take that back. I have a positive number, and then I have a negative times a negative, so this is going to be a positive. So this number is just going to become more positive. So in this case, delta G is going to be a positive number, no matter what T is. Because I had this minus times a minus, this changes into a plus. So this will always be positive. So this equation will never, or this reaction I should say, will never be spontaneous. Okay, and I can stop. 17D then, to wrap up number 17, my delta H is negative 419.4 kilojoule, which is the same as negative 419,400 joule. My delta S is negative 114.1 joule per K. So my delta G is my H, negative 419,400 joule minus T times negative 114.1 joule per K. All right, in this case I have a negative value, and then I'm going to end up adding something because these two negatives will turn into a positive. So I'm not sure if G in the end is going to be negative or positive. So I need to find the value for T where G will be negative. So I can take this part of the equation and set it less than 0. And then solve for T. Okay, so I'll keep my left side as negative 419,400 joules. And I'm going to add this term to both sides. So keep my less than sign, then add this term to both sides. So I end up with T times negative 114.1 joule per K. Then I'm going to divide both sides by this term, negative 114.1 joule per K. Divide this by negative 114.1 joule per K. So over here, this all cancels out, and I'm left with T by itself on the right. And if I do this math, let's see, I end up with 3676 Okay. So hold on for 1 minute, I'm looking. I missed a sign on my work. Okay, so as long as the temperature is greater than 3,676 Kelvin, this reaction will be spontaneous. Any other case, it won't be. Okay, then finally, number 18, which of the following is not zero for an element in its natural phase? The standard enthalpy of formation, the absolute entropy, or the standard Gibbs free energy of formation. Well, all of our formation values are always zero for an element in its natural phase because it doesn't take any energy to form something in its natural phase. So the answer here is absolute entropy. Okay, 19, you and a friend are going to a store. So we're both here, we're going to the store. I take this path, you take a very roundabout path, but we both end up at the store. We leave at the same time, we each take a different route to get there. You arrive before your friend, so I arrive before you. Which of the following is a state function? The path we traveled, the time it took us to get there, or the destination? Well, the destination is the state function. This is very similar to the example in the book of the mountain, and there was a windy road getting to the top of the mountain, or someone who hiked directly there. So a state function, it doesn't matter how you get there as long as this is where you end up. So the destination is the state function. And then number 20, finally, we have a physical process in a system cools its surroundings and it's spontaneous. So it cools the surroundings. So what does that tell us? That tells us that the surroundings are becoming more organized. Becoming more organized. Okay, so the entropy is actually decreasing because entropy is disorganization. So the disorganization is decreasing. The surroundings are becoming more organized, but it tells us at the same time it's also spontaneous. Well, the only way for something to be spontaneous is if we add the entropy of the surroundings and the entropy of the system and get a value less than zero. This is what Gibbs free energy tells us, that it's only spontaneous when the entropy of the surroundings plus the entropy of the system is less than zero. Well, we know our surroundings are becoming more organized. So that means our system has to become much less organized, which means that it's an increase in entropy. Okay? So what was the question asking? Does it result in an increase or a decrease of entropy for the system? Well, the entropy for the system must be increasing. The entropy of the surroundings is decreasing. So the only way for this to be less than zero is if the entropy of the system is actually increasing. Okay, so that is all the problems, practice problems, or I'm sorry, the review questions. So stay tuned for the new material for chapter 15. If you have any questions about 14 that could benefit the entire class, go ahead and post them out on Google Classroom. Thanks.